Okay. So let's get started. We're a little bit behind the other group. All right, let's turn to page 16 of our notes. We're going to do a little bit of review here, and we're going to talk about something new. So let's turn to page 16 of our notes. And we've had this baby problem before. The weight of newborn babies, okay, linear function, okay. Use the regression capabilities on your calculator to find a linear model of the form y equals a plus bx. Now remember, there are two linear choices on your in your stat calc menu. He is specifically asking for this one. I truly don't think it matters, but this is the one you want, so that's the one we'll go with. So we'll go to stat edit. We're going to put in all these numbers. And then when we're all done putting them in, we'll go to stat calc. We'll choose that regression. And I got 3.34 plus 0.8x. What's going on back there, Celeste?
I spilled my water bottle.
That's okay.
Sorry.
It's over water. Just make sure no one slips in it.
Yeah.
All right, so letter A says, use the regression capabilities of your calculator to find a linear model. Okay. You good? Are you okay? Then B says, use the model to predict the weight of the baby 2.5 months after birth. So we're going to find the weight of that baby 2.5 months after birth. I got 5.34. What is that? Kilograms? Is that what you got? And then the review question says, the actual weight of the baby 2.5 months after birth was 5.5. So this is what our model said. So this was our prediction. Somebody actually weighed the baby and it was 5.5. So we want to find the residual. Who remembers how to find the residual again? How do we do that? Oh, we need to remember this. Residual is actual minus the predicted. And remember, the predicted is what your model says. So we've got 5.5 minus 5.34. So our residual is, no. Oh yeah, is that right? 0.16 kilograms? Did our model underestimate or overestimate the weight of the baby? Underestimated the weight of the baby. Okay, now that's review. We've done that before. Here's the new stuff. If a model for a given set of data is appropriate, the residual plot should appear without pattern. All right, so let's look at some examples. Example 3. An exponential regression was used to model a data set. The residual plot is shown. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on this plot? So read through those choices, tell me what you think. What do you think? C, the exponential model is appropriate because the residuals show no real pattern. They're just kind of dotted around in there. All right, example 4. A group of kids used a set of data to create a linear, quadratic, and exponential regression. After creating them, the students plotted the residuals for each model type. Based on what you see, which model was most appropriate for the data? Do you think the linear model, the quadratic model, or the exponential model was best? Exponential, because there's no real trend there, just bouncing all over the place. All right, read example 5. Tell me what you think. Anybody want to throw out an idea? Hey Charlie, I'm tossing the ball to you because you're always good for an idea.
I'm just gonna go with exponential because that's what it said the last question.
Okay. Good try, but I don't think so. Celeste?
I said linear because the more circles there are, the more paint comes in.
And that would be true if all the circles were the same size. It has to be quadratic. And it's quadratic because he's painting circles. What's the formula for the area of a circle? Pi r what? Square. That's quadratic. That's quadratic. So yes, we need a quadratic model for that. We need a quadratic model. After creating the model, he buys different paint colors to use. In this situation, do you think it's more appropriate for the model to underestimate or overestimate the actual amount of paint needed? Over, because if he runs out. So we want it to overestimate, but not by too much, because we don't want to spend a lot of extra money, but we want it to overestimate. Okay, let's turn to page 18. Page 18, here we go. Data for a random sample of high school students is shown in the scatter plot. Notice that the data is corresponding the number of absences with GPA. How would you describe the relationship between the number of absences and the student's GPA?
More absences, the lower the GPA.
Yeah, which makes perfectly good sense, but that's what the data shows, right? See that trend? Yep. Does the data seem to suggest a linear, quadratic, or exponential model? How do you know?
Linear.
Definitely linear, I would think. I mean, isn't the data, and I know it's kind of scattered, but like if you took a big thick marker, wouldn't that be in a line? Those data points? All right, somebody worked it out and got the equation. So somebody put all that data in and got the equation. Where X is the number of absences and Y is the student's GPA. So somebody did a linear regression, which was our guess. That is the regression they came up with. Do you think, does the residual plot bear that out as being appropriate? Yeah, that line through the center, that's 0. So the ones on top are positive residuals and the ones on the bottom are negative residuals. Aren't they pretty well balanced? And they're, yeah, all the way down the line. So yeah, I think it's great. What does this mean? This would be the slope of the model. What does that number mean? Charlie?
It means that, like, well, isn't it like anytime you plug in X, it's gonna get smaller because a bigger X is gonna get smaller because it's, or wait, no, I'm thinking of something else.
No, what you said is right. It doesn't really address the question, but what you said was accurate. What does that stand for? The number of absences. Look at your graph. The x-axis says number of absences, right? So every absence is going to result in your GPA dropping by 0.0146. So you were right, Charlie, big picture. Every absence is going to result in a loss in GPA of 0.0146. So negative 0.0146 GPA points per absence. Remember, slope is a rate of change. Use the regression model to predict the GPA of a student who has 23 absences. Let's just plug in 23. And we can do that. You get 3.19916, so about 3.20. I don't know if I typed that in right. Is that what you got? Too many digits. Is that okay? All right, 2.6 will be due on Thursday. And now I have a little fun exercise here for you. Let's see. Why don't we take a few minutes and see how far you and your partner, if you don't have a partner, you can work in groups if you want. We'll go in order. So let's try A through D. And when you're done with those, you can move on, but I want to get A through D up here on the board so we can talk about them. So go ahead, do A through D, get them up here on the board, and then you can do more. on, just skip it and go on. I want to get through as many of these as we can today.
Oh.
It's definitely not gonna be 3,000 times, like I said, yes.
So you do this to a 1 7. Was it front?
Oh, that's okay.
1.4. And then this is yeah, fractional exponent. But you're doing that, and that's what that means. 1.4 to the 1 7. I mean, I think other. Is this what like? Because our answers do that. And you like. I don't know. Yeah, I skipped it. That's what you had originally, but then that's when you bring the 1 7. That's what we talked about. I'm pretty sure that's when you bring the 1 7. Well, it matters either one. And that's what. If it specifies. But it is functional.
Yes, exactly.
I mean, I don't think it really. I mean, yeah, but it's the same thing. 1.4 to the 1 7. I don't know. But I think it's
I thought you said mine. Oh, you said it. You're throwing your voice now, aren't you? What? David's. for a party, right? Yeah. I mean, I don't know.
I let it be like one.
That is awesome. Oh, I thought you were talking about oh, yeah, nice.
Anybody got any of them yet? A, B, or D? You guys got which one? All right, C is gonna be done. All right, anybody have an A you can put up there for us? You got an A, good deal. How about B and D? Anybody have a B and a D?
I got B.
B, perfect. Then I need a D. Who's working on the mice? Sam, how you guys doing up there? Did you get D, the mouse problem?
That's what we're doing.
Evan, what about you guys? Did you
I
get
don't
mouse
like
problem?
60 was 6
Right.
But then I thought it was 3 months. Oh, 60. 3 months and 60. So you do 2. 0, 6, and 3, 60. So that's what you use. We did 30.
I like it.
So yeah, it's basically 10 to 130. So it's that. And then you see what I'm saying? It's like 6,
Year, yeah, first year, next year, you took it back. Why do you think I'm wrong for being
Okay, let's look at what's up here. I love everything that's up here. It's all wonderful. So for problem A, problem A, part A, did you just multiply 3,200 times 1.4? Yeah, is that okay with everyone? And then write an equation. A 40% growth would be 1.40. That would be our base, and the starting was 3,200. But that 1.40 happened over a period of 7 years. So we can't just put an X here because that's not what's going on. That is 7 years. So we have to do what we did yesterday and divide it by 7, which is exactly what our sorry, I'm going to write letter. Is that okay with everybody? Perfect, good job. And then we used this formula, this thing, and got 3,696 tigers. And so did I. Anybody have a question about A? Feel okay about that? Okay, B. Charlie went through all the work and did such a magnificent job. I just did a regression on my calculator and came up with the same thing, only mine, Charlie, because you used your geometric formula, which is 100% okay. Yours looks like this. Mine looks like this. To the X. So I had to, you back up to here, I had to back up one door to get the zeros term. So 3.9 divided by this 2.78 gives me that number. So this is what my calculator says. This is what Charlie said, and he was right. Either one is right. Beautiful, beautiful job. Oh man, I love this. Did anybody catch that? Catch this? Leo said, okay, in 71.5 years, my stuff decreases by 1 over 32, 1/32. Well, I know that 1/32 is 1/2 to the 5th, which is significant because we're doing half-life. So he said I got 175 times 1/2 to the 5 over 5t over 71.5, and then he reduced that and got 14.3. That is awesome. I didn't do that. I didn't even, until I got my answer, that never even popped into my head. That's wonderful, you know. What I did is I just worked it out. I took the equation that was given and set it equal to half of 175 and solved for t. Got exactly the same answer. Way more work, exactly the same answer. Good thinking. And then D, might not be able to see it because it's under the TV. This is what she came up with. Celeste?
Is it okay if we already took the cube roots and put 2.154?
Absolutely, absolutely. Yep. And in some ways, this is better even, Celeste, because in a straight exponential, we like our exponent to be x, but we have talked about, you can change that exponent by altering, so that, yeah, that's great, that's great.
Isn't it 6?
Oh, yeah. You had 6, I wrote 60, thank you. Yes. Okay? All right, I told you this was fun. All right, let's go. Let's do E through H. E through H. let's see if we can get some, new volunteers.
Do you have an idea? Looking like one. Where you can plug in one.
It is not good.
Where you can plug in one.
Get two, it's not.
Yeah. Oh. I didn't realize that it was a different scale. So full right here.
That is 4.
You get 3, 4,
Oh. Drive it. Okay, you're on the right track.
You get,
Figure it out.
I really think it's not good. I put it in my calculator. What did you use for the time? Yeah, so the first one. I know. So you're 0.
Oh, wait. Look, it's gonna be. Six. Yeah, exactly. Like, but how much is that quarter year percentage?
Did you get? Oh yeah. Yeah. But I just want
It's 1980.
Okay, let's talk about the first one. Did anybody find any of them that are correct equations for that curve? Did you find any? Which one? 3? I think 3 is okay. And what I did, I don't know what you did, but I know from the picture the y-intercept is 4. So I just put in 0. And if it gave me 4, then I knew I was on the right track. And then if I put in 1, I should get 2. And then I thought I'm okay. All right, so 3 is a good one. Anybody find another one that's a good one? 4? And I use the same logic, that's all I did. When I did nothing magical there. Did you find any others? 6? Now notice when you put in 0, you get 1/2 to the negative second, which is 4. And when you put in 1, you get 1/2 to the negative first, which is 2. I think 6 is a good one. I think so. How about 7? Isn't 7 the same as 3? Is the same as 3, so it matches. So that's what I had. 3, 4, 6, and 7. Did you cross any of them out right from the beginning? I hope you crossed out number 2 because that is exponential growth. That idea. And then I hope you crossed out, what is that, 8? Because 8 is upside down. And when you have an upside down exponential, where is it? Under the x-axis. So it can't, those two could move, can't be those two. And then with a little checking, it's not 1 or 5. You okay? All right, let's look at F. see exactly what is done up there. I'm a little bit bothered by A. Help me think through this. Should I be bothered by A? What's up there is basically slope. And what do I know about this situation that I have? It's exponential. So I think we need to redo A. Did anybody have a different idea how to do it? Leo, what did you think about doing?
So I said 1981 as the original, whereas
Zero.
0. And so then A would be 3.35. So I did 3.35 times B to the 35th plus 9. I divided 9 by 3.35 and then took the 35th root of it.
Okay, yes, that's right. Why did I do? Oh Lord, someday you'll all get old. For some reason I did the 25th root. I don't know how to subtract right, but yeah, that's what I did too. I remember. So we're multiplying 35 times to get from 3.35 to 9. So he divided those two numbers to find the total multiplication, and then for 35th rooted it. Does that make sense to you? And then we could use that to receive, and then everybody okay? Alright. G, the eighth problem. That's what I have. Does that look okay to everybody for G? If we are growing 7/8 of its size, that's 0.875 added to 1, so 1.875. That is a pretty good growth rate. And then since it's 2.5 days, it's another 2.5 days. And then, yeah. Criminal model underestimated by 4483. Did you read that? Alright, quickly, let's look at the next one. We're almost out of time. So, let's look at K real quick. We're not gonna have time to come back to this sheet. Let's look at K real quick. Somebody made a linear regression and then did a residual plot. What do you think? Was the linear model a good one? No. And again, is there a pattern to that residual? And that is what we don't want. We want this kind of thing, right? That's what we want. We don't have it. Alright, so I'll leave you to work on that for the next 4 minutes. I haven't done them, but you can compare with each other. I'm happy to walk through one with you if you want. Be careful with J. I see it's upside down. Are you working in the chat?